Okay, Houston, we've had a problem here.
This is Houston. Say again, please.
Houston, we've had a problem.
Houston, we have dropped. Houston. Houston, we don't have a problem. Today we're going to talk about energy transformation. So remember, we're talking about like the study of what's called thermochemistry, how things work sort of energetically as we do stuff. So there are two key terms we want to define, or let me start over. Houston, we don't have a problem. Today, we want to talk about something called energy transformation. What the heck is that? Well, it turns out that there are two types of reactions. Now, in class, we've really talked about this, but if you don't recall, there's something called exothermic and endothermic, and it really is the study of something called thermochemistry. Now, think you've got this. Thermo means heat, so it's the energy. It's like what happens energetically in a chemical reaction. Now we've seen that. You guys have lit me on fire. We have done lots of interesting reactions where we've made bombs, but we really haven't like studied the science of the energy behind chemistry. So thermochemistry, thermal chemistry. It makes sense, right? So exothermic and endothermic are two key terms. Yeah, it's a study of the chemical changes in chemical reactions. So let's talk about energy. Now, energy is kind of a weird thing. It isn't a thing. I can't weigh 15 grams of energy. Energy, it's different. The universe really can be divided from a scientific perspective, I guess you could say, into matter, and that's what we've been studying a lot of. You know, those are atoms and molecules and things like that, and energy. And though they're connected, they're not the same thing. So energy, by definition, is the capacity to do work or to supply. So energy, what's energy? Well, energy is this. It is the capacity to do work or to supply heat. All right, so if you can do work, you can roll the ball up the hill as the image shows right there. That is doing work, but also supplying heat. If you burn something, it produces heat. That heat can then be used, actually oftentimes, for many, many other things. Now, keep this in mind. Heat has no mass. That you can't weigh, 500 calories. You can't do that, okay? Now, you say, wait a second, Mr. Bergmann, calories, that measures heat? Well, but I ate a chocolate bar, and I ate that chocolate bar for lunch, and it had so many calories in it. When it burned, it produced those calories in your body, but it isn't those calories. It has those calories in it. That makes sense? So, like, speaking of a bar, right? Now, you probably remember this from previous science classes. There's two kinds of energy, potential energy and kinetic energy. And in this class, since it's a chemistry class, we're going to study chemical potential energy. Now, so this is the energy in that bar, that food that you ate. It's the energy stored in the structural units of the chemical substance. So in a chemical, right? So even my hand, there's energy in my hand. We're not going to eat my hand. That would be nasty. Gross. It is that there is energy stored in that, and specifically they're stored in the chemical bonds. So when an atom A is connected to atom B, that bond has energy. And it turns out that when you break a bond, it releases energy. And when you form a bond, it absorbs energy. Make sense? Break, it releases. That makes sense, doesn't it? And it takes energy to form a bond. All right? And that leads us to two key terms, what's called exothermic and endothermic. All right? So, which leads us to an interesting conversation, and this is a conversation about what we call systems. So when we talk about a systems, in the science world, we can talk about the system. It's really the part of the universe, if you will, that we want to study. And in our case, usually that means it's a chemical reaction or some kind of a physical change. So if I've got a flask that I want to study, the system typically is what's inside the flask. So here's kind of a diagram. Sketch this out here, right? The surrounding is everything else in the universe around the system. So to kind of illustrate this, let's make the system the flask, right? The system is the flask, and then the surrounding is everything on the outside. So this is going to help us understand, because we have to talk about the direction of energy flow. It's a very important conversation, is what direction does energy flow from and to? So, and you can't lose energy, right? So the law of conservation of energy from this old dead white guy, it says that energy can't be created or destroyed, just transformed. So if I've got energy stored in a chocolate bar or chocolate chip cookie, I can't change the energy, but I can change it from one form to the other. I can change it into heat. So I'm in a room and I'm moving my body right here. So the energy, the food that I ate this morning or last night or whatever, is being transformed into heat to warm my body, but also into mechanical energy that helps me to move my hands, etc., etc., right? So let's talk about something intriguing. A little cut to a video clip because it tells us something very interesting. So an interesting thought experiment. If it's colder on the other side of this door, and I open the door, and it starts to get colder, what's happening? Is the cold air coming in, making my room colder, or what? Now, something important to understand is that energy always flows from hot to cold. And maybe your mom has told you this, or your dad, or is that when you open the door, they'll say, quit letting all the cold air in. And respectfully, you're going to say, actually, Mom, that's not how it works. What actually happened is that when I open the door, the hot air, heat always travels from hot to cold. The hot air in the room heats up the outside, which makes this room cold because the molecules slow down. So even though it does get colder here in the room, it's getting colder because these molecules are heating up the outside, which is slowing the molecules down, which causes it to cool down because heat always travels from hot to cold. So we live in Houston here, right? In Houston, what you would expect is it's going to be hot, right? So this is we live in a hot place, and I'm sitting next to the ice machine of the science department, right? So if I pull out here, I've got ice, so that's cold. So an interesting thing, a question for you, right? If I were to like stick my head in here, would that ultimately make me cold, right? Let's say, I live in Houston, which is a crazy hot place, and as I live in this crazy hot place and I want to cool off, is that a good technique? Sticking my head in there on a hot day, maybe went for a run or something like that. Well, it turns out that actually it doesn't. How come? So then how does an ice machine or refrigerator work? I don't know if you ever realized this, but if you take your hand and you put it behind the refrigerator, okay, you're going to discover that it's hot, warm. So what's happening in an ice machine or a refrigerator or freezer is it's moving the energy away from the inside, here where the ice is, and then it's taking that energy behind it through something called a compressor that heats that up, and then that's what causes an ice machine to work. Because energy has to flow hot to cold. So how do you make something cold? Is you remove the heat by finding something that's cold that the air can heat up, which cools the air that it leaves. An interesting question, if you were to say, I want to cool down my house by just open up the refrigerator, what you'll actually do is you'll heat up your house. Wait, how come? Because the energy that will go out the back of the refrigerator will be more than the cooling energy of the ice machine. So you will actually make your electricity bill go up, so to speak, because you'll have to run the AC more. So do not just open up your refrigerator thinking that it will cool you off. It will actually heat you up, at least in the long run. This is super important to understand, is that energy can only flow in one direction. It always flows from hot to cold. It can never flow from cold to hot, right? Like we said, when you step outside in the cold day, what you're doing is you're letting the hot air out. You're not letting the cold air in, or the refrigerator that we just saw. So it always flows in the same direction. Or another way to say it is from high to low. It can never do the reverse. Ever, never, ever do the reverse. So you might have noticed that we've been talking at the top of this, it's been saying exothermic and endothermic, and I haven't really discussed what that is. So what is exothermic? Exothermic is when the energy is released into the surroundings, right? Because remember, we've got the system and the surroundings. So what happens is it leaves the system and goes to the surroundings. Typically what happens in an exothermic chemical reaction is it's going to heat things up. Okay, most of the reactions that we've seen that are kind of interesting have been ones that heat things up. So the example here, this picture of a fire, a furnace or something like that, that is highly exothermic. In fact, let's watch an exothermic reaction. Endothermic is really the opposite of exothermic. Endo, inside of. So in this case, energy is absorbed into the system. And so what typically happens is things get colder. So in this particular picture, this is an example of a reaction that as it happens, it gets colder and colder and colder. And for it to get colder, that means the energy is actually being absorbed into the system, all right? And they tend to get cold. Let's take an example of that. Now let's talk about something that's kind of weird. I want to talk about the difference between two key words, and this is something that can really confuse students. Heat and temperature, they're not the same thing. Heat and temperature are not the same thing. What do I mean by that? Heat is a measure of the total energy. Temperature is a measure of the average kinetic energy. So we've said this earlier, but temperature is equal to an average kinetic energy. Make sense? That's the average of all the molecules and basically how fast they're going. But heat is all the energy. So I have two examples right here, or a thought question. Heat is all the energy. I've said that right. Okay. And we've got two pictures here. We got picture number one, we've got a large lake. Picture number two, we've got a hot cup of steaming coffee. Which of those has more heat in it? Now, the answer almost everybody says is they say it's the coffee, and that's wrong. Because the coffee is so small. Now, the average, the temperature's higher, right? Like boiling point would be 100 degrees Celsius, but because there's so much liquid in the lake wins, by far. The total amount of energy in a lake is way more than the total amount of energy in a cup of coffee, okay? Because this is the average. This is the average. I mean, here's an interesting sort of story, and maybe you know this, but if you climb up in the atmosphere, it gets colder, right? If you were flying in a big plane, it's very, very cold if you were to step out. But there's actually a layer of the atmosphere at the very top called the thermosphere. Actually, not quite the top, close to the top. And it's super hot. Like it's like 500 degrees or something crazy hot. But if you were to step out of your spaceship or your airplane that's super flying way high up there, kind of on the edge of space, you know what would happen? You would freeze to death, even though it's like 500 degrees. Does that make sense? No, it doesn't. But it does because you see what happens is way, 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 way up there, there is very, very few molecules. Even though they are moving very, very fast and they're very, very hot, because there's not enough heat to keep you warm, you would freeze to death. Because you need heat to keep you warm versus them moving so fast. Now, so oftentimes they go together, but in the thermosphere, they do not go together. So when we talk about chemical reactions, here's kind of how we draw them, right? So energy, we have a chemical reaction, and energy goes, we say, on the right side. So here we have a chemical reaction. CH4 plus 2O2 plus CO2 plus H2O. And then what we say, and here's a term you haven't seen before, the energy in a reaction is called the delta H, okay? The change in H, heat. It's actually got a fancy term called enthalpy, not important. But in this case, we can see what the energy is. But I also want you to notice, what do you see right here? Do you notice that right here, that we've got a negative sign? So if it's a negative sign, that means it goes on the right. So essentially what we have is we have a reaction here, and we've got this number that's negative 902. But we want to actually put that into the reaction. So when we put that into the reaction, what we do is we say plus 902 kilojoules. Now I want you to notice something. The 902 is not negative. Here it's negative. Over here. Here it's negative. Okay, so if it's here it's negative, I put it positive because you can't have negative energy. But when you have a negative sign, what that means is that it is a product. It's produced. And later on we're going to learn how we can do some math with these types of reactions. But if it's exothermic, it's going to have a negative value of the delta H. The triangle means delta, change in heat. And it goes on the right side of the. And if it's endothermic, I bet you get the idea, then energy goes on the left side. It's a reactant in the equation. So here's a reaction. 2NH3 makes 3H2 plus N2. And the delta H for this one is 76.7 kilojoules per mole. And so if I'm going to write this into the equation, right up here, I'm not going to put it here. I'm going to put it over here. I'm going to say plus, and I'm going to say 76.7 kilojoules. So my full reaction is this thing right here, right? 76.7 kilojoules plus 2NH3 makes 3 H2s and N2. So we're adding something to our chemical reactions that isn't a thing, it isn't matter, but it's energy. Make sense? So if it's endothermic, notice again, the delta H here is positive. If it's positive, you put it on the left side of the reaction. If it's negative, you put it on the right side of the reaction. Endothermic typically get colder. Those are the ones that are going to be on the left side. Exothermic reactions, you're going to find the energy at some number on the right side. And every reaction gives off different amounts of energy. And as a note, when it says 76.7 kilojoules, notice, actually, another thing to make, a note here. It says 76.7 kilojoules right here, but it says kilojoules per mole. Notice I did not write per mole here. This is actually kilojoules per whatever the reaction is. Does that make sense? So it's technically per 2 moles of ammonia, per 3 moles of hydrogen, and per 1 mole of nitrogen. So we're going to just put kilojoules in here because the moles is built into the balanced chemical. And lastly, we want to talk about reactions. And there's kind of a graph that helps us understand there's two kinds of, there's exothermic and endothermic reactions. So for an endothermic reaction, we draw a graph that looks like this, where this side right here is the potential energy, PE. And right here, we have what we call the reaction. Remember, the abbreviation for reaction is RXN, progress. So as the reaction progresses, you might start at this amount of energy. So right here, at this point, this is the energy of the reactants. All right? And then as the reaction begins, and we've seen lots of chemical reactions happen, what happens is the graph, whoop, zippers up. And then what usually it goes through the top, and then it flattens out. And over here, and the reaction is done, this is the energy of the products. Make sense? Now, we've got some interesting other things that we can measure. So actually, if I would, let's say that this is 100 kilojoules. And right here, we have 300 kilojoules. And actually right here, we're talking about that second. Let's say that's 350 kilojoules. That make sense? So you got some numbers. So when you go from the reactants to the products, if we go right here to here, the change, this is actually delta H. The delta H is how much energy between the reactants and the products. The reactants and the products. And in this case, this one would be, we went from 100 to 300. In this case, that would be equal to 200 kilojoules. And it would be positive because we went up. But you say, what's up with the extra hump at the top, Mr. Bergmann? Well, it turns out that oftentimes a reaction doesn't get started until you add some extra energy. And so right here, this right here would be considered from here to here. Once you get here, the reaction is just going to proceed, but you sometimes have to add energy. This is called the E sub A. So what the heck is the E sub A? That is called the activation energy, which is the energy it takes to get the reaction started. So once you get up to here, boom, you can find the reaction's going to just kind of run downhill, and it's just going to happen by itself. By the way, what would that be in this case? It starts at 100, it goes to 350, so that would be 250. So that would be 250 kilojoules. So note that this is for, like it says right here, this is for an endothermic reaction. For an exothermic reaction, it's going. In an exothermic reaction, again, you're sketching these graphs out. Let's just draw the same exact coordinates. You've got the potential energy here. We've got the reaction progress down here. And what have we got going on here? The graph is actually going to look kind of backwards. Maybe you can kind of figure this out. Usually what happens is you're going to start here. Oh, that's not such a good color, is it? You're going to start here, and this is the reactants. And then you go here, that's your activation energy, and it comes like here, and here's your products. And your delta H is here to here, and that's going to be a negative number. Again, so let's say that this is 400, this here is 100, and this right here is 50. So the delta H would be 400. This would be equal to negative 300 because it goes down kilojoules. The activation energy, E sub A, which is actually just this height right here, that would be equal to I said 450. This would be equal to 50 kilojoules per mole. So ladies and gentlemen, energy transformations have to do with this concept called exothermic, endothermic reactions. Houston, we don't know.
Okay, Houston, we've had a problem here.
This is Houston. Say again, please.
Houston, we've had a problem.